Hello, my name is Mark Zhao, and I will be talking about SHEF, Shielded Enclaves for Cloud FPGAs. This work was done in collaboration with Mingyu and Christos Kozyrakis. So let's begin by asking what the three biggest trends in systems and computer architecture are today. Well, if we can use Hennessy and Patterson's 2018 Turing lecture as insights, it's these. First, there's a focus around security, especially hardware security mechanisms that address the increase in our trusted computing base, or TCB size. Secondly, the need for domain-specific accelerators that provide high performance and efficiency to address the end-of-general scaling in Moore's law. And finally, a massive shift towards pay-as-you-go cloud platforms that provide instant scalability and availability. The focus of this work also follows Hennessy and Patterson's insight, and asks, can we use cloud FPGAs to address all of these three trends? Namely, can we enable secure cloud accelerators? But before we answer that, let's look at what the options are today for enabling secure accelerated cloud computing. Well, option one is to use CPU Trusted Execution Environments, or TEEs, in the cloud. This is great because it reduces the TCB to only the hardware itself, but current TEEs don't support hardware accelerators. Option 2 is to simply use cloud accelerators like GPUs, TPUs, or FPGAs, but this requires users to trade off security as a result. Finally, option 3 is for users to build their own on-prem infrastructure, which allows them to provide acceleration and moderate security, but they lose the advantages of the cloud as a result. Unfortunately, there's no option that enables all three goals. What's more is that I like to motivate two additional goals we need. The first is configurability. This need arises because just like performance requirements differ, threat models also differ across applications. For example, a secure database may need high throughput random accesses and read and write a large range of memory multiple times, while a Bitcoin miner just needs a relatively small input and output, the block and nonce, for example. What this means is that the security solution we need for each accelerator is completely different. For the database, we'll need something that secures DRAM and potentially uses heavy integrity verification like Merkle trees. For the Bitcoin miner, we can use something much more lightweight like simple authenticated encryption on a register interface. This flexibility is important, and it's not possible on current TEEs which have fixed security mechanisms. Secondly, we also need a solution that's easily adoptable, meaning that it's able to be implemented on current cloud infrastructure and hardware, and easy to implement by users. Our solution for all of these demands is SHEF. SHEF is an end-to-end framework for custom accelerators on cloud FPGAs that provides a workflow to enable comprehensive, trusted execution environments. It requires no hardware changes from current cloud FPGAs, while also providing a tailor-made and transparent solution to meet the security and performance requirements of diverse accelerators. So let's walk through the threat model that SHEF assumes. The SHEF workflow specifies 4 parties. The manufacturer is trusted and is in charge of building the physical FPGA device. The FPGA is placed into an untrusted cloud service provider's infrastructure, who offers the FPGA for rent. The cloud provider can also run untrusted logic on the FPGA and untrusted infrastructure around the FPGA device. The accelerator will run on the FPGA device, is developed by a trusted IP vendor, and licensed for use. Finally, data owners rent the FPGA instance and IP and use the accelerator to process sensitive data. We assume that the data owner trusts the manufacturer and IP vendor, but not the cloud provider. The next question to ask is, how do we enable TEEs on cloud FPGAs? Well, we can break TEEs down into key building blocks that we have to enable. First, we need an asymmetric key in hardware that provides a root of trust. A secure boot mechanism then loads the program or accelerator into a known and trusted state. A remote attestation protocol proves the state to a remote user, who then loads sensitive data into the TEE via a secure storage and I/O mechanism. And finally, the user runs the accelerator, which is secured during runtime by an isolated execution mechanism. Finally, as we discussed before, accelerator TEEs must be customizable for the hardware and the application. Unfortunately, there's a number of challenges that makes enabling these building blocks difficult on current FPGAs. First, there's a lack of hardware keys to build a root of trust, which is a foundation for secure boot and remote attestation. Secondly, programming and testing FPGAs, as well as securing their I/O and execution, are complicated by the presence of a shell operating system. Finally, there's simply a lack of customizable security mechanisms for FPGAs today. Now, let's go into these challenges in detail. The first challenge is that current FPGAs assume a completely different threat model with only a single trusted user that has physical access to the FPGA before deploying it in an untrusted environment. This is opposed to infrastructure as a service deployment, which allows multiple users to use the same FPGA device, which is provisioned and deployed in an untrusted facility. As a result, current FPGA devices only offer an AES key, not an asymmetric key that is necessary for the root of trust. The second challenge is that the current cloud FPGAs use a shell module, which is untrusted FPGA logic that acts like an operating system for the cloud provider. The challenge is that the cloud provider controls the shell, which monitors and controls all I/O to the accelerator, as well as untrusted software and infrastructure users have to use to access the accelerator. Given the spatial architecture of FPGAs, how do we securely boot an accelerator or provision data in and out of it given the shell? Finally, the last challenge is that no customizable hardware security mechanisms exist today. Specifically, we want to allow users, that is, data owners and IP vendors, to customize the end-to-end workflow, and also recall from earlier that we want them to be able to customize both the security mechanisms used by and the performance of their accelerator. So how does SHEF address these challenges? To answer that, we first have to understand what SHEF is. SHEF has two main components. First, it is a set of firmware that implements key protocols that we propose, namely around building a root of trust, secure boot, and remote attestation. Secondly, SHEF provides a library of customizable RTL modules that we call the shield. These modules are used by the IP vendor to enable secure storage and I/O, as well as isolated execution for their accelerator. The first challenge to address is how do we build a root of trust from current hardware? The insight that we make is that we can extend the current hardware AES key into a symmetric key in software. To securely do this, we first require the manufacturer to burn a device-specific AES key into available eFuses within a module in current FPGAs called the security processor block. Then they provision a second asymmetric device key into the firmware of the SPB and encrypt the firmware with the AES device key. Finally, they can deploy the FPGA, which now contains a secure root of trust, into the cloud provider server. The second challenge to address is how to securely program both the accelerator and use it to process sensitive data given the untrusted shell and cloud infrastructure. To do so, we rely on two SHEF components. First, the SHEF security kernel, which runs from a dedicated processor, triggers a remote attestation protocol with the IP vendor. Through this protocol, the security kernel receives the encrypted accelerator IP, securely decrypts it, and programs both the accelerator and the shell onto the FPGA. The second component is the shield, which the IP vendor integrated into the accelerator IP. The shield transparently secures the accelerator and data provided by the data owner during runtime. It transparently provides authenticated encryption by interposing on the current AXI interfaces that exist between the shell and the shield, meaning that the accelerator can simply operate on unencrypted data as before. It's able to securely relay data between the data owner and the accelerator via a data encryption key that was loaded into the shield as part of the remote attestation protocol. For more details on these protocols, please see our paper. The last challenge to address is customizability. We can see how the shield provides customization by looking into its microarchitecture. Users can choose to use two different shield interfaces that provide authenticated encryption. A register interface provides memory mapped register accesses, or a memory interface provides high bandwidth access to device memory in HBM or DRAM. Both of these interfaces are highly customizable. Users can customize security in the form of cryptographic engines, key sizes, encryption block sizes, and integrity verification mechanisms. For example, this allows users to avoid having to implement expensive tree-based integrity schemes if they only have a region of read-only memory. The shield is also parameterized, which means that users can quickly adjust on-chip cache sizes or parallelism to improve performance. This customization can even be done at address-level granularity as we map each set of customized security modules to specific regions of memory. So that gives an overview of SHEF. Let's talk about how we implemented it. We implemented SHEF in two ways. First, we built an end-to-end implementation on a local UltraScale Plus FPGA board. This included implementing the hardware root of trust into the SPB firmware, the security kernel which implements secure boot and remote attestation, and also the shield. Because we had full control of the FPGA, we could implement the end-to-end SHEF workflow and showcase its security. Then we evaluated SHEF on an UltraScale Plus FPGA in the cloud, namely AWS F1 instances. While we couldn't fully implement the boot process on these, we showcased how the shield connects to the cloud provider's shell. This allowed us to evaluate SHEF's end-to-end performance trade-offs during runtime, which we'll talk about next. So now let's first look at the runtime overheads the shield introduces while adding security to 5 diverse benchmarks. We first answer the question, is SHEF performant? For each benchmark, we configure the shield with 4 configurations. This is easily done through editing a parameter in the shield. We use 2 AES key sizes, 128 and 256 bits, with the larger providing more security. We also used 2 different levels of shield parallelism, 4x and 16x. We have an additional configuration for DNN Weaver, as we'll discuss later. The y-axis shows the execution time of the secure accelerator normalized to the execution time of the unsecure version. This means 100%, shown by the red line, means that the shield adds no performance overheads while also adding security. We see that for the Bitcoin benchmark, we observe no overheads. This is because Bitcoin has a high arithmetic intensity where the only I/O is small registers, which Bitcoin does a lot of compute on. This is similar for convolution, which we further optimize for by using large encryption chunks to reduce authentication overheads because it simply streams in large batches from memory. For digit recognition and affine transformation, we see that increasing AES parallelism from right to left helps reduce performance trade-offs. This is in contrast to DNN Weaver, where we see that increasing encryption parallelism doesn't help because it uses small reads that are authentication bound. Here we can leverage the modularity of the shield and swap out the HMAC module we use for a PMAC module, which allows us to increase the authentication parallelism, which further reduces overheads. Finally, we show the area costs of the shield on the AWS F1 FPGA of the largest shield configuration for each benchmark. We observed that the area costs of the shield were below 11% across all benchmarks, with lookup tables being the most used resource by the shield. This emphasizes that the shield is able to provide both low performance overheads and low area overheads while enabling secure accelerators in the cloud. Finally, let's walk through an end-to-end example of how we can apply the SHEF workflow to an important application. To demonstrate this, we use a recent work that proposes GDPR-compliant storage nodes as an example. This work calls for FPGA-enabled storage nodes that provide encryption at rest and encrypted channels, assuming that the storage nodes are securely provisioned. We can apply SHEF here by enabling each storage node with SHEF. Then, the security kernel's secure boot and remote attestation protocols allow for these storage nodes to verify themselves with compute nodes and to the control plane. This allows the control plane to securely provision sensitive data and user keys into each storage node. Then during runtime, the shield can provide encryption at rest, as well as encrypted channels to connect storage nodes to remote compute nodes and users. We also wanted to evaluate if SHEF can do this with low overheads. To answer this, we built a key value store benchmark to model the storage node. We then demonstrated that by configuring the shield parallelism, we can reach minimal performance overheads of 20% with less than 5% of area costs on AWS F1 instances. With increasing area, we further expect to be able to reduce throughput overheads. So in conclusion, we argue that there is a need for flexible, trusted execution on hardware accelerators. This is not a simple solution to enable on current hardware. However, SHEF addresses this need with an end-to-end workflow that enables T building blocks without any hardware changes. We provide a customizable shield that can meet the diverse security and performance requirements of FPGA accelerators, and also do so with limited performance and area overheads. If you'd like to learn more, please feel free to reach out to us at the email here, and we will be soon releasing our code on GitHub. Thank you all for your time.